February 3rd, 1943. Berlin Tempelhof, Telefunken Research Laboratories, Germany. Professor Leo Brandt's hands slightly trembled as he lifted the copper cylinder from its protective case. He was examining what would later be called the most significant intelligence failure in Nazi radar development. The device, no larger than a coffee mug, and weighing barely 3 kg, contradicted everything German physicists had calculated about microwave radar technology. "This cannot be generating such power at 3 gigahertz an hour," he exclaimed. "Our mathematics proved such power levels impossible at these wavelengths." Just 24 hours earlier, a Royal Air Force Sterling bomber was shot down near Rotterdam by Luftwaffe night fighters. The aircraft was part of the Pathfinder force and carried equipment so secret it included self-destruct charges, which were designed to obliterate the technology before it could be captured by the enemy. Those charges had failed. German recovery teams found the radar system largely intact. Its copper magnetron was still warm from operation. What German scientists discovered when they examined that device would expose a technological gap so profound that it would force the German leadership to confront an uncomfortable reality. The Allies were not just ahead, but operating in an entirely different realm of physics. The capture of that single component would reveal that Germany was not fighting the same technological war. They were years behind in understanding how to harness the power of centimetric wavelengths. The story of this technological chasm began not with a defeat, but with a decision made at the height of German military triumph. Following the spectacular fall of France in June 1940, with Britain seemingly isolated and vulnerable, Adolf Hitler issued a decree that would handicap German science for the duration of the war. The Führer decreed that no scientific research project could receive priority funding unless it promised definitive military results by 1942, approximately 2 years from the directive. This single administrative decision, born from overconfidence in a swift victory, would cost Germany its technological edge in the most crucial electronic warfare development of the conflict. The decree effectively killed long-term radar research in Germany, just as British scientists were making breakthroughs that would change warfare forever. The magnetron. Theory versus reality. Dr. Wilhelm Runge, head of radar development at Telefunken, had clearly seen the mathematical limitations. German scientists understood the theoretical principles of cavity magnetrons. Hans Hollmann had even filed a patent for a multi-cavity design on November 27, 1935, years before the British work. His United States patent, $2,123,728, was granted on July 12, 1938, describing a magnetron with multiple segments connected by straps to increase efficiency. Soviet physicists Nikolai Alexeyev and Dmitry Malurov had published research on cavity magnetrons in Leningrad in 1936, work that German scientists had reviewed. The theory was not secret. International physics journals had carried articles on magnetron development throughout the 1930s. What eluded German engineers, however, was the practical implementation at high power levels and stable frequencies. German calculations, performed by some of the Reich's most capable physicists, suggested that magnetrons operating above 1 non-text, gigahertz, would be fundamentally unstable, prone to frequency drift that would make them useless for precision radar applications. Experimental prototypes built in German laboratories had validated these concerns. The devices either failed to oscillate at the desired frequencies or produced such low power outputs, perhaps $30 to 50 ITEX-W, that they seemed impractical for military applications. Based on these calculations and experimental results, and reinforced by the urgency of wartime production demands, German radar development committed entirely to lower frequencies where established technology functioned reliably. By 1942, German radar systems operated primarily between $90 and $600 text-to-imaging, using klystron tubes and specialized triodes that German industry could manufacture consistently. These systems worked admirably for their intended purpose. The technology was mature, understood, and producible at scale, but they required antenna arrays measured in meters and provided resolution measured in hundreds of meters. For early warning and general aircraft tracking, these limitations were acceptable. For precision applications, However, they represented fundamental constraints that German engineers believed were unavoidable given the laws of physics as they understood them. German radar systems, the Würzburg radar represented the pinnacle of German tracking radar technology, operating at a 53 text (Comdoberler) wavelength with a 3 text (Embraer) parabolic dish antenna manufactured by the Zeppelin Company. It could track aircraft with acceptable accuracy at a 40 text kilometers range. The system used a conical scanning technique introduced in the Würzburg D model in 1941, employing an offset receiver feed called a quirl that rotated at 25 text Hertz. This provided an angular resolution of approximately 0.2 section in azimuth and 0.3 section in elevation, sufficient for directing night fighters toward bomber formations, but not precise enough for direct gun laying without optical assistance. The larger Würzburg Riese, the giant Würzburg, represented Germany's most advanced operational radar. Based on the same receiver circuitry and displays as the D model, the Riese featured a much larger 7.4 textadiers-meter parabolic antenna and a more powerful transmitter. This extended maximum range to 70 text kilometers against aircraft targets, with the improved angular accuracy needed for direct gun laying. The system was too large for mobile deployment and was typically mounted on railway flat cars as the Würzburg Riese E variant. Approximately $1,500 of these systems were produced during the war, forming the backbone of German air defense, Freya early warning radars. Operating at wavelengths between $2.5 and 2.3 textdiameter, provided long-range detection capabilities that complemented Würzburg's precision tracking. With a peak power output of $15 to 20 textm and a pulse repetition frequency of 500 textm, Freya could detect approaching bomber formations at ranges up to 160 text km. The system could not accurately determine altitude, but it provided early warning that allowed Würzburg stations to be alerted and night fighters to be scrambled. Together, these systems formed the Himmelbett line defense network that had inflicted substantial losses on RAF Bomber Command throughout 1941 and 1942, the cracks in German confidence in their radar. Superiority was not without foundation. The Wehrmacht had deployed radar earlier and more extensively than any military except the British. German radar-directed anti-aircraft fire was more effective than anything the Allies could match in 1941 and early 1942. The night fighter defense system, using ground-controlled interception guided by Würzburg radar, had achieved remarkable success rates. German engineers looked at their radar network with justified pride. They had built effective, reliable systems using sound engineering principles. What they didn't know was that British scientists had transcended the limitations German theory declared absolute. That confidence began eroding in late 1942. Bomber command losses, which had been climbing steadily as German night fighter tactics improved and radar coverage expanded, suddenly began diverging in ways that troubled German air defense analysts. British bombers seemed able to navigate with precision through heavy cloud cover and darkness. They found targets in conditions that should have made navigation impossible without visual reference to ground features. Pathfinder aircraft marked objectives with accuracy that suggested they possessed navigational aids superior to anything Germany had fielded. Intelligence reports mentioned mysterious new equipment, but captured air crews provided no information. British aircrew were under strict orders regarding new radar technology. Knowing that capture of the devices intact could compromise Allied superiority that had been years in development, aircrew were briefed that $2 equipment was so valuable that its loss to the enemy could change the course of the war. Instructions were clear: reveal nothing, even under interrogation. The self-destruct charges installed in $2 units were designed to trigger automatically on severe impact or could be manually activated if capture seemed imminent. In December 1942, German signals intelligence detected unusual radio emissions from RAF bombers during raids. The signals were brief, pulsed transmissions at frequencies around 3 text Bergatz, corresponding to wavelengths near 9 text kilometers. German radio engineers who examined the intercept reports dismissed the initial findings. No one could generate useful power at such frequencies, the physicists insisted. The laws of physics, as understood by German researchers, made high-power centimetric radar impractical. The emissions must be some form of electronic countermeasure, perhaps a decoy transmitter, or possibly navigational beacons on the ground being interrogated by airborne receivers. They could not be operational radar because that would require power outputs German theory indicated were unachievable. The first operational raid and the crash on January 30th, 1943, RAF Bomber Command conducted its first operational mission using the new 2SS ground mapping radar. 13 aircraft equipped with the centimetric radar from Pathfinder Force marked targets in Hamburg. Actually, only 6 aircraft completed the marking mission, as 7 had to turn back with technical difficulties. The raid succeeded despite weather conditions that would have scattered conventional bombing. Observers noted the precision of the attack despite 10/10 cloud cover. The Pathfinders had marked the target with incendiary indicators, and 100 Lancasters that followed bombed using these visual markers. For the first time, RAF bombers had found and marked a target in complete darkness and total cloud cover, using only electronic navigation. The Luftwaffe achieved several interceptions during the Hamburg raid. One bomber was shot down, but the 2SS equipment aboard was destroyed in the crash and subsequent fire. German investigators found fragments of unusual radio equipment in the wreckage, but nothing that revealed the system's full capability or operating principles. They were looking at pieces of the most advanced radar technology in existence and did not recognize what they were seeing. The fragments showed evidence of centimetric wavelength components, but without a complete system, German analysts could not determine the purpose or capabilities of the equipment. 4 days later, on the night of February 2nd and 3rd, 1943, the technological revelation arrived in a field near Rotterdam. The RAF conducted a raid on the Pernis oil refineries near Rotterdam. Short Sterling Mark III bomber, $9264, serial number MGL, nicknamed Life for a Love, from No. 7 Squadron, Pathfinder Force, was returning from a bombing mission to Cologne when it was intercepted. Oberleutnant Hans-Dieter Frank of 2 NJG-1, flying a Messerschmitt Bf-110 from Gilse Ryan Airfield, closed on the bomber in darkness. Ground-controlled interception using Würzburg radar had vectored the night fighter to the bomber's position. Feldwebel Wilhelm Goeth, Frank's radar operator, confirmed the target on their Liechtenstein airborne radar. The engagement was textbook. Frank positioned his Bf-110 below and behind the Sterling, in the blind spot where the bomber's defensive guns could not engage. A burst from the upward-firing cannon struck the bomber's fuselage and wing. The Sterling went down trailing fire, crashing at 22:21 hours near Hendrik Ido Ambacht, approximately 3 in text $100 from the village of Herjansdam. The impact was severe but not catastrophic. The aircraft did not explode on impact, though fire quickly spread through the wreckage. German recovery teams reached the crash site before dawn. 5 crew members had been killed in the crash, including squadron leader William Arthur Smith. 2 crew members survived and were taken prisoner. In the shattered nose section of the bomber, recovery personnel found equipment unlike anything in German experience. A rotating parabolic antenna barely 60 $60 in diameter was connected to an electronic chassis that included a circular cathode ray tube display showing a plan position indicator format. The display unit had been destroyed in the crash, the glass tube shattered, and internal components damaged beyond repair. But the transmitter section survived largely intact, protected by its robust copper construction. At the heart of the transmitter was that copper cylinder, machined with extraordinary precision, containing 8 symmetrical cavities arranged around a central cathode. The device was labeled with British military markings and the designation CV64. It was sealed, self-contained, with no external power connections beyond the primary electrical feed and a simple output coupling. The engineering was elegant, almost deceptively simple in appearance. Yet the precision of manufacturing was immediately apparent, even to initial examination. This was not experimental equipment hastily assembled in a laboratory. This was production hardware designed for reliability and manufactured to exacting standards. The Rotterdam Device, General Lieutenant Wolfgang Martini, head of Luftwaffe Signals Intelligence, arrived at the crash site later that morning. Martini was not merely an administrator, but a trained engineer who understood radar technology. He had followed German radar development closely and was familiar with the theoretical limitations that had guided German research priorities. When he examined the captured equipment, he understood immediately that this was significant. The equipment was compact beyond anything German radar could achieve. The antenna was far too small for operation at frequencies Germans considered practical for high-power applications. Yet this was clearly sophisticated technology, not some experimental oddity that had failed under operational conditions. This was a working system that had been operating successfully when the bomber was shot down. Martini ordered the equipment transported under armed guard to Telefunken's Berlin laboratories. The magnetron was packed with extraordinary care. Guards accompanied the transport throughout the journey. The importance of the capture was immediately recognized at the highest levels of Luftwaffe command. This was not routine battlefield salvage, but a potential intelligence windfall that could reveal Allied technological capabilities. Professor Leo Brandt received the recovered components on February 3rd at Telefunken's facilities in Berlin-Tempelhof. Brandt, born in 1908, had worked as a high-frequency engineer at Telefunken since 1932. He was recognized as one of Germany's leading experts in radio frequency technology. His team worked through the night of February 3rd and 4th, meticulously documenting the device before attempting any testing. Every dimension was measured. Every component was photographed from multiple angles. Detailed sketches were made of the internal structure visible through inspection ports. X-ray examination revealed the internal cavity structure and cathode assembly. The team worked with scientific precision, documenting everything because they understood they might have only one opportunity to examine this technology. What they found in those initial hours stunned them. The magnetron was a sealed unit, entirely self-contained with no external magnets. German magnetron designs, including Hollmann's patented versions, required separate powerful electromagnets to generate the magnetic field necessary for operation. These electromagnets were large, heavy, and required substantial electrical power. This device had permanent magnets built into its structure, integrated directly into the copper block housing. The magnets appeared to be made from cobalt steel alloys, materials that provided magnetic field strength German researchers had considered impossible to achieve with permanent magnets. The engineering was elegant to the point of appearing simple, but the precision required was extraordinary. Tolerances were measured in hundreds of a millimeter. The 8 cavities were machined into solid copper blocks, not assembled from separate components. Each cavity was identical to the others within measurement precision. The cathode, running along the central axis, was coated with an oxide compound that German researchers recognized as an electron-emitting surface, but of a type German industry had not successfully manufactured. The vacuum seals used techniques that German manufacturers had attempted but not mastered for production units. Every gasket, every junction, every mechanical interface showed evidence of manufacturing processes refined through extensive production experience. On February 4th, Brandt's team prepared to power the magnetron. They built a custom pulse generator to provide the high-voltage electrical pulses needed for operation. The team had no documentation, no operating instructions, no specifications. They had to infer the operating parameters from examination of the device and from general principles of magnetron operation. They expected, based on German experience with magnetron development, perhaps $100 text $2 output at best, possibly at frequencies around $500 text matches. They thought they understood the limitations of the technology. When the magnetron was powered for the first time in a German laboratory, it produced approximately 10 kilowatts of pulsed power at precisely 3 gigahertz. The output was stable, repeatable, and far exceeded what German theory predicted as possible. The measurement instruments available in the laboratory were designed for much lower power levels. They had to improvise measuring techniques, using attenuators to reduce the signal to levels their equipment could handle, then calculating back to determine the actual output power. Every measurement confirmed the same incomprehensible reality. This thumb-sized device generated more microwave power than German laboratory equipment filling entire rooms could produce, and it did so with an efficiency German theory suggested was unattainable at these frequencies. Brandt wrote in his initial report, preserved in German archives and later captured by Allied intelligence teams, that the British had achieved in practice what German mathematics declared impossible. The report's tone was professional, clinical even, but the implications were clear to anyone who read it. Germany's understanding of microwave physics was incomplete. The theoretical frameworks that had guided German research had led them away from a technology that was not only practical, but had been in operational use by the enemy for an unknown period. Engineers measured the magnetron's performance over several days of testing. The output frequency was remarkably stable, varying less than 1 dollars across multiple tests. The frequency stability was achieved through the physical dimensions of the cavities themselves, which acted as resonant structures. German magnetrons using Hollmann's design suffered from frequency drift as the device heated during operation, thermal expansion changing the electrical properties of the oscillating system. The British design minimized this through careful engineering of the mechanical structure and choice of materials with appropriate thermal expansion coefficients. Every measurement revealed another layer of sophisticated engineering. The wavelength was equally shocking from a military application standpoint. 9 text dollars corresponded to 3 on text gigahertz frequency. At this wavelength, a small antenna could provide resolution that would require antenna arrays tens of meters across at frequencies Germany used. The implications for airborne radar were immediate and devastating. The British could build radar systems compact enough for single-engine fighters, with resolution fine enough to detect individual buildings from high altitude. They could create ground-mapping radar that showed coastlines, rivers, cities, and terrain features with clarity impossible at longer wavelengths. They could detect submarine conning towers, night fighters, and ships with precision that made German longer wavelength radar seem primitive by comparison. German radar development had dismissed centimetric wavelengths as impractical, precisely because they could not generate sufficient power. The entire German radar research program had been built on the assumption that high-power microwave generation was impossible, or at least impractical for military applications. The British had solved that problem 3 years earlier, in February 1940, when John Randall and Harry Boot at Birmingham University produced their first working prototype, generating 400 text $8 at 9 text meter wavelength. By May 1940, they had improved that to over 1 text to kilowatts. By late 1940, General Electric Company engineers at Wembley had increased output to 10 text kilowatts, and by 1941, production magnetrons were achieving over $100 text kilowatts in pulsed operation, the AGR and the intelligence windfall on. February 5th, a conference was convened at Luftwaffe headquarters in Berlin. The meeting was classified at the highest level. Present were General Oberst Martini, Professor Brandt, representatives from Telefunken, Siemens, and GEMA, the major German electronics firms, plus air defense commanders and Luftwaffe technical staff. The mood was somber. Brandt presented his findings methodically, using technical language and precise measurements, but the conclusions were inescapable. The British cavity magnetron represented not an incremental advance, but a fundamental technological breakthrough that Germany had missed entirely. German scientists had worked on magnetron designs. Hollmann's patents proved German researchers understood the basic principles, but German research had abandoned high-power microwave development because mathematical models indicated it was not feasible within wartime timescales. Resources were limited. Industry was strained. Priority went to improving existing systems rather than pursuing speculative technologies that physicists said would not work. The British had not just solved the engineering challenges, they had been operating centimetric radar operationally for months, possibly years, while Germany remained convinced such technology was theoretically impossible, or at minimum years away from practical implementation. The conference reviewed what was known about British radar deployment. The Würzburg system had successfully intercepted numerous RAF bombers. Recovery teams had examined wreckage and found no evidence of advanced radar equipment in aircraft shot down before January 1943. This suggested the $2 deployment was recent, but intelligence from other sources painted a more troubling picture. Reports from U-boat commanders described being surprised by aircraft attacks in conditions where detection should have been impossible. Marine intelligence had noted increasing Allied success in locating surfaced submarines. Luftwaffe bomber crews reported being intercepted by British night fighters with suspicious frequency. The conference participants began connecting disparate intelligence reports into a coherent picture. The British had developed not just one centimetric radar system, but an entire family of applications: ground mapping radar for bomber navigation, air-to-surface vessel radar for submarine detection, airborne interception radar for night fighters, and possibly a gun-laying radar for anti-aircraft systems. Each application used the same basic technology, the cavity magnetron, adapted for specific military purposes. The British had not achieved one breakthrough. They had created an entire new category of radar technology. While Germany was still perfecting longer wavelength systems, the captured system was given the designation Rotterdam Device, the Rotterdam Device, named for the location of the crash. A working group formed immediately, the Arbeitsgemeinschaft Rotterdam, abbreviated AGR. The group's mandate was threefold. First, understand how the British magnetron achieved its performance. Second, develop countermeasures against centimetric radar to protect German forces. And third, begin German development of equivalent technology to close the gap the British had opened. Each objective faced substantial obstacles that would prove increasingly difficult to overcome as the war situation deteriorated. The roadblocks, too. Replication understanding the magnetron required reverse engineering manufacturing processes Germany had not developed. The device used oxide-coated cathodes, requiring specific materials and processing techniques. German vacuum tube manufacturers had attempted to produce similar cathodes but had not achieved consistent results in production. The British had clearly solved the manufacturing problems through years of development and production experience. The permanent magnets required cobalt, a strategic material Germany had in limited supply. Before Operation Barbarossa, Germany had received cobalt from Soviet sources. But that supply was cut off when Germany invaded the USSR. Turkish imports partially compensated, but supplies remained insufficient for large-scale production. Even the vacuum sealing techniques were unfamiliar to German manufacturers. The magnetron had to maintain high vacuum over an extended operating life while withstanding vibration, temperature changes, and the mechanical stress of operational use. German vacuum tube manufacturing used glass envelopes with metal-to-glass seals, techniques perfected over decades for radio tubes. The British magnetron used all-metal construction with ceramic insulators, requiring entirely different manufacturing approaches. Every aspect of the device revealed engineering refinements that came only from extended production experience. On February 22nd and 23rd, the Arbeitsgemeinschaft Rotterdam held its first formal two-day meeting at Telefunken's offices in Berlin. Present were representatives from Germany's electronics industry, Luftwaffe technical services, university researchers, and radar specialists from operational units. The group examined the magnetron in exhaustive detail, passing the device around the conference table, taking measurements with calipers and micrometers, making sketches, and discussing manufacturing challenges. The atmosphere was professionally subdued. These were experienced engineers and physicists who understood exactly what they were looking at and what it meant. The consensus was sobering. Germany could copy the British design. German machine shops, given proper tooling and sufficient time, could manufacture components to the required tolerances. German material scientists could develop equivalent cathode coatings. German metallurgists could create permanent magnets approaching British performance. But production would require diverting resources from existing programs that were already struggling to meet Wehrmacht demands. Manufacturing capacity for precision components was strained to breaking. Machine tools were operating multiple shifts. Skilled workers were in short supply, increasingly being drafted for military service. Raw materials were allocated months in advance to existing priority programs. Introducing entirely new production processes for unfamiliar technology would take many months at minimum, possibly over a year, before meaningful production quantities could be achieved. Dr. Otto Hachenberg, a young Telefunken engineer assigned to the AGR project, later recalled the atmosphere in those early meetings during a 1973 interview conducted by Woodruff Sullivan for the National Radio Astronomy Observatory. The interview was part of Sullivan's research for his book on early radio astronomy. Hachenberg, who had worked on recovering and analyzing radar equipment from crashed Allied aircraft during the war, described the psychological impact of examining the British technology. We were examining equipment that proved British engineers had solved problems we had declared unsolvable. Every aspect of the design revealed thoughtful engineering matured through experimentation we had never conducted. This was not prototype equipment cobbled together in a laboratory. This was production hardware, implying the British had been manufacturing these devices in quantity. We were studying what appeared to be the third or fourth generation of their development, while we had not begun serious work on the first generation. The revelation was compounded when interrogators interviewed the surviving crew members from the downed Sterling. Initially, the two prisoners provided only name, rank, and serial number as required by the Geneva Convention. They had been extensively briefed on the importance of the $2 system and understood that no information should be disclosed. RAF Bomber Command had emphasized during briefings that $2 represented years of British research investment and that its capture by Germany could compromise Allied bombing effectiveness. Aircrew were told that under no circumstances should they discuss the radar system's capabilities, operating principles, or deployment status. However, over subsequent days and weeks, German interrogators skillfully extracted key details. The Luftwaffe Interrogation Center, Auerstel West at Oberursel near Frankfurt, employed experienced interrogators who used sophisticated psychological techniques. The interrogators did not resort to physical coercion, which was generally counterproductive with Allied aircrew and violated Wehrmacht policy. Instead, they used a combination of isolation, seemingly casual conversation, planted false information to elicit corrections, and careful psychological pressure applied over extended periods. From these interrogations, German intelligence learned critical information. The system was called $2, though the prisoners did not know the origin of the designation. It provided a map-like display of ground features below the aircraft, showing coastlines, cities, rivers, and terrain. The radar had been in operational service since late January 1943, only days before this particular aircraft was shot down. Most alarmingly, the crew indicated this wasn't experimental equipment assigned to a few select aircraft. Bomber Command was in the process of fitting $2 to the entire Pathfinder force initially, with plans to eventually equip all heavy bombers. The prisoners' information suggested British production capacity was sufficient to manufacture these devices in hundreds, possibly thousands. The scale of British centimetric radar deployment became clearer as intelligence accumulated through February and March. 1943, multiple sources of information began converging into a comprehensive picture. Signals intelligence detected $2 transmissions from increasing numbers of RAF bombers. The distinctive pulse characteristics and frequency range became identifiable. The U-boat crisis and centimetric ASV marine reports documented increasing U-boat losses in the Atlantic, with submarines being attacked by aircraft in conditions where detection by previous generation radar should have been impossible. Submarines were being caught surfaced at night in complete darkness, attacked before they could crash dive to safety. The magnetron technology was not limited to bombing radar. Coastal Command aircraft were using centimetric ASV Mark III radar to detect surfaced submarines. The same cavity magnetron that provided $9 text camera wavelength for $2's ground mapping could detect submarine conning towers and periscopes at ranges that longer wavelength radar could not match. The narrow beam width possible at centimetric wavelengths provided angle accuracy sufficient to guide aircraft directly to submarines before detection was possible using German METOX radar detectors, which were tuned to detect the longer wavelengths of ASV Mark II radar U-boat losses in the Atlantic, had been climbing mysteriously throughout late 1942 and early 1943. Admiral Karl Dönitz, commanding U-boat forces, had noted with concern that submarines were being caught on the surface with increasing frequency. U-boat commanders reported being attacked by aircraft that appeared suddenly, providing no warning that allowed time to dive. The METOX detector, which had previously provided effective warning of approaching ASV-equipped aircraft, was failing to detect these new attacks. The explanation was now clear. British aircraft were hunting submarines using ASV Mark III centimetric radar that German boats could not detect with existing equipment. The air interception gap British night fighters were also equipped with centimetric AI radar designated AI Mark E8, far superior to German Liechtenstein systems. German Liechtenstein Fuji 202 operated at 61 text-to-camera wavelength and required large $32 element Matratze antenna arrays that created significant aerodynamic drag and reduced aircraft speed by $20 to 30 Text-km/h. The later Liechtenstein SN2 used a lower frequency to avoid British jamming, but required even larger $8 element Hirschgeweih antenna arrays that slowed aircraft by 50 Text-km/h. The British centimetric AI used compact dish antennas barely 1 text in diameter and provided superior target resolution with minimal aerodynamic penalty. RAF night fighters equipped with AI Mark VIII had been decimating German bomber raids over Britain throughout early 1943, and Luftwaffe intelligence had attributed this to improved ground-controlled interception tactics and searchlight cooperation. The real reason was radar that could locate German bombers with precision German technology could not match. The destruction and replacement on March 1, 1943, the situation took an ironic turn that would be almost comedic if the stakes were not so serious. During a major RAF raid on Berlin, British bombs struck Telefunken's Berlin facility where the Rotterdam Device was being analyzed. The building suffered severe damage. The captured magnetron was destroyed, blown to fragments by the explosion. The working group lost its only complete sample just as they were beginning to understand its construction and preparing to attempt production copies. The loss was devastating. Weeks of careful analysis, documentation, and reverse engineering planning seemed wasted. Then, extraordinarily, that same raid provided a replacement. Handley Page Halifax II, $17,877, serial TLO from No. 35 Squadron, was shot down by Lieutenant August Geiger near Marlow in the Netherlands. The Halifax crashed with another $2 unit aboard. Recovery teams found the equipment in better condition than the Rotterdam Device, with much of the display system intact along with a complete magnetron. The odds of losing one sample to bombing and gaining another on the same night were astronomical, but it illustrated the scale of British $2 deployment. RF Bomber Command was equipping aircraft with this advanced technology at a rate suggesting substantial manufacturing capacity existed. German scientists immediately set to work analyzing the second unit. The device was essentially identical to the Rotterdam Device, confirming these were production units manufactured to standard specifications rather than hand-built prototypes. The production challenge Telefunken was tasked with producing German copies, designated LMS-10, Laufzeitröhre mit Magnetsteuerung, transit time tube with magnetic control, based on the British CV64 design. The copying process revealed layer upon layer of British engineering sophistication that would challenge German manufacturing capabilities. Every component required manufacturing, processes that German industry had to develop from scratch or significantly improve. Precision machining, the cavity dimensions, had to be machined to extraordinary precision. Tolerances of 0.01 Tau text-to-amps or better were required to achieve proper resonance at the operating frequency. German machine shops, accustomed to tolerances of 0.1 Haar text-amp for most radar components, were not equipped for such precision work on the required scale. New milling machines with better bearings and more rigid construction had to be procured. Precision measuring instruments had to be calibrated. Machinists had to be trained in techniques they had not previously needed. The entire manufacturing process required improvements. German industry struggled to implement while simultaneously dealing with Allied bombing disruption. Cathodes and vacuum seals there. Oxide-coated cathodes required materials and processes that the German chemical industry had not perfected. British cathodes used barium and strontium oxide coatings applied at high temperatures in precisely controlled atmospheres. The coating had to be uniform, adherent, and produce consistent electron emission properties. German attempts to produce similar cathodes had been partially successful in laboratories, but had not achieved the consistency needed for production units. British manufacturers clearly had years of production experience refining the process. Britain had been working with American firms, particularly Western Electric and General Electric, that had decades of experience with vacuum tube manufacturing for communications and broadcasting applications. When Britain shared cavity magnetron technology with the United States through the TZAD mission in September 1940, American manufacturers had rapidly scaled up production using manufacturing expertise gained through years of commercial vacuum tube production. The cobalt crisis, TIA, permanent magnets, presented perhaps the greatest material challenge. British magnetrons use cobalt steel alloys, likely Alnico type, to create powerful permanent magnets integrated directly into the tube structure. These magnets provided the magnetic field strength of several thousand Gauss necessary for proper magnetron. Operation. Germany faced critical cobalt shortages that affected all high-temperature alloy production. Cobalt was essential for turbine blades in aircraft engines, cutting tools for machine shops, and various steel alloys used in weapons production. Every ton of cobalt allocated to magnetron magnets was a ton unavailable for these competing uses. German engineers experimented with alternative magnetic materials, but none provided the required field strength. The elegance of the British design, with integrated permanent magnets requiring no power and having no failure modes, was impossible to replicate with German materials. In a bitter irony, engineers began salvaging permanent magnets from other crashed British aircraft to complete their magnetron copies. German production units were being completed using British-manufactured components cannibalized from battlefield salvage, a situation that underscored the industrial limitations Germany faced, production, disparity, and countermeasures. May 1943, Telefunken had completed 4 LMS-10 magnetrons, painstaking copies of the British CV64 design. These represented 3 months of intensive work by some of Germany's best engineers. 4 tubes total. Meanwhile, according to captured documents recovered after the war, Britain was producing approximately $200 cavity magnetrons per month by mid-1943, and American production was reaching similar levels. The disparity was not just technological, it was industrial, reflecting fundamentally different manufacturing capacities and resource availability. The AGR pursued parallel efforts on countermeasures against centimetric radar. The detection effort proved relatively straightforward. Crystal detectors tuned to 9-dihexamer wavelengths could pick up $2 transmissions at considerable range. By April 1943, German engineers had developed a prototype detector system designated Fuji 350 Naxos Z, named after the Greek island Naxos. The device used a rotating direction-finding loop antenna and a receiver that covered the frequency range $2,500 to 3,750,000 text per dollar, encompassing the $2 as operating frequency. Detection range was approximately 35 text per km. Naxos entered operational service in September 1943, allowing night fighters to home toward $2 emission sources. However, Naxos was fundamentally reactive technology, relying entirely on British bombers transmitting. British intelligence soon learned of Naxos. After detailed analysis showed losses did not significantly increase, the RAF concluded $2 benefits outweighed the risks and continued full deployment. British engineers immediately began developing countermeasures, including a 3-text Kemidawa H, $2 Mark III that would operate outside. Naxos's detection range, German efforts at developing indigenous centimetric radar moved forward slowly through 1943 and 1944, projects like the Fuji 240. Berlin airborne interception radar faced mounting obstacles. The comparison with British and American capabilities became clearer as more intelligence arrived. The T's admission had given the US the magnetron technology in September 1940. American industrial capacity had rapidly mobilized, establishing the Radiation Laboratory, RadLab, at MIT, and scaling up production to thousands of magnetrons per month. The magnetron that German scientists examined with such care was one of tens of thousands being manufactured. The fundamental gap. Difference represented not just years of development time, but entirely different approaches to industrial organization and quality control. British magnetrons came off production lines with performance specifications guaranteed by manufacturing process control. German magnetron development remained in the experimental stage, producing hand-built prototypes that required individual tuning and adjustment. The technological gap extended beyond the magnetron itself to supporting technologies. Plan Position Indicator, PPI displays. British radar used these map-like displays. German radar relied on A-scope displays, which were less intuitive. Automatic tracking. British systems incorporated servo mechanisms to keep antennas locked on targets without manual operator control. German systems required manual tracking, .tr switches. British radar used gas discharge tubes to allow a single antenna for both transmit and receive, protecting sensitive receivers. German engineers were years behind in practical implementation. The explanation for this comprehensive failure lay in different strategic decisions. British prioritization. Britain had made radar development the top national priority from 1935 onward, investing substantial funding and infrastructure. The Hitler Decree of 1940. Limiting research funding to projects promising results by 1942 was devastating for the long term. Patient experimental work required for the cavity magnetron. German centimetric wavelength programs were defunded or reduced in priority precisely when British programs were achieving breakthroughs. By summer 1943, the full scope of Allied centimetric radar deployment was apparent. H-2S enabled precision bombing, ASV Mark III made the Atlantic progressively more dangerous for U-boats, and centimetric AI was inflicting unsustainable losses on German bombers. The disparity was a comprehensive failure in scientific industrial mobilization for a technology whose military significance was not recognized until Britain had already achieved an insurmountable lead. German attempts to close the gap continued through late 1943 and 1944. But circumstances were increasingly unfavorable as Allied bombing disrupted German industrial production systematically, material shortages worsened, and skilled workers were conscripted for combat units. Features. The radar had been in operational service since late January 1943, only days before this particular aircraft was shot down. Most alarmingly, the crew indicated this was not experimental equipment assigned to a few select aircraft. Bomber Command was in the process of fitting $2 to the entire Pathfinder force initially, with plans to eventually equip all heavy bombers. The prisoner's information suggested British production capacity was sufficient to manufacture these devices in hundreds, possibly thousands. The scale of British centimetric radar deployment became clearer as intelligence accumulated through February and March 1943. Multiple sources of information began converging into a comprehensive picture. Signals intelligence detected $2 transmissions from increasing numbers of RAF bombers. The distinctive pulse characteristics and frequency range became identifiable. Marine reports documented increasing U-boat losses in the Atlantic, with submarines being attacked by aircraft in conditions where detection by previous generation radar should have been impossible. Submarines were being caught surfaced at night in complete darkness, attacked before they could crash dive to safety. The magnetron technology was not limited to bombing radar. Coastal Command aircraft were using centimetric ASV Mark III radar to detect surfaced submarines. The same cavity magnetron that provided 9 Dalbert text $$ wavelength for $2 ground mapping could detect submarine conning towers and periscopes at ranges that longer wavelength radar could not match. The narrow beam width possible at centimetric wavelengths provided angle accuracy sufficient to guide aircraft directly to submarines before detection was possible using German METOX radar detectors, which were tuned to detect the longer wavelengths of ASV Mark II radar. U-boat losses had been climbing mysteriously. Admiral Karl Dönitz, commanding U-boat forces, had noted with concern that submarines were being caught on the surface with increasing frequency, attacked by aircraft that appeared suddenly, providing no warning. The explanation was now clear. British aircraft were hunting submarines using ASV Mark III centimetric radar that German boats could not detect with existing equipment. British night fighters were also equipped with centimetric AI radar, designated AI Mark VIII, far superior to German Liechtenstein systems. German Liechtenstein Fuji 202 operated at 61 text kint wavelength and required large $32 element matrazi antenna arrays that created significant aerodynamic drag. The later Liechtenstein SN2 used lower frequency but required even larger $8 element Hirschgeweih antenna arrays that slowed aircraft by 50 text kilometers $. British centimetric AI used compact dish antennas barely 1 centimeter textmalers in diameter and provided superior target resolution with minimal aerodynamic penalty. RAF night fighters equipped with AI Mark VIII had been decimating German bomber raids over Britain throughout early 1943 due to radar that could locate German bombers with precision German technology could not match. The second capture and production struggle. On March 1, 1943, the situation took an ironic turn. During a major RAF raid on Berlin, British bombs struck Telefunken's facility where the Rotterdam Device was being analyzed. The captured magnetron was destroyed, blown to fragments. Then, that same raid provided a replacement. A Handley Page Halifax II was shot down near Marlow in the Netherlands, carrying another $2 unit. Recovery teams found the equipment in better condition, with a complete magnetron. The odds of losing one sample to bombing and gaining another on the same night were astronomical, but it illustrated the scale of British $2 deployment. German scientists immediately set to work analyzing the second unit, confirming these were production units manufactured to standard specifications. Telefunken was tasked with producing German copies, designated LMS-10 based on the British CV64 design. The copying process revealed layers of British engineering sophistication that severely challenged German manufacturing. Precision machining. Cavity dimensions required tolerances of MathBF DO02 text, MEM-Ds or better. German machine shops, accustomed to tolerances of 0.1 don text UMMAR for most radar components, struggled. Cathodes and vacuum seals. The oxide-coated cathodes required specific materials and processing techniques that German industry had not perfected for production. The cobalt crisis. The permanent magnets required cobalt steel alloys, a strategic material in short supply for Germany. German engineers began salvaging permanent magnets from crashed British aircraft to complete their magnetron copies, a stark sign of industrial limitation. By May 1943, Telefunken had produced approximately 20 magnetron copies, compared to over $10,000 produced by British and American industry. The disparity was not just technological. It was industrial, countermeasures and deterioration. The Arbeitsgemeinschaft Rotterdam, AGR, pursued countermeasures. By April 1943, German engineers developed a prototype detector system designated Fuji 350 Naxos Z, which could pick up $2 transmissions at approximately 35 I Textafhain Klontutaler. Naxos entered operational service in September 1943, allowing night fighter crews to home on $2 emissions. However, Naxos was reactive technology, relying on British bombers transmitting. British intelligence eventually noted the risk, but concluded $2 benefits outweighed the risks and continued full deployment. German efforts to develop indigenous centimetric radar moved slowly. Projects like the FUG 240 Berlin Airborne Interception Radar remained in extended testing, encountering reliability problems. Production of operational systems remained perpetually 6 months away as obstacles mounted. Allied bombing disrupted German industrial production systematically, targeting electronics manufacturing facilities. Material shortages worsened, affecting cobalt, tungsten, copper, and aluminum. Skilled worker, conscription. Engineers and technicians were drafted for combat units, removing specialized knowledge from factories. In April 1945, Telefunken finally began delivering production FUG 240 Berlin night fighter radars. The system used German-built magnetrons based on captured British designs and provided capabilities roughly equivalent to British centimetric AI from 1942, 3 years earlier. About 25 units were installed in Junkers Ju-88 night fighters before the war ended in May 1945. The decade gap, the gap in radar physics, was not metaphorical. It was literal. German centimetric radar in 1945 equaled British capability from early 1942, representing a 3-year lag in calendar time but reflecting fundamental differences in technological approach and industrial capacity. The post-war assessment found that German radar research was effective in areas where Germany had invested consistently, like the Würzburg and Freya systems. But in centimetric wavelengths, German research had effectively stopped in 1940-1941. Dr. Otto Hachenberg, who worked on the Rotterdam Device project, later became a distinguished radio astronomer. He acknowledged the German failure, stating, "We knew the principles. What we lacked was the sustained commitment to develop theory into practice. We calculated that success was unlikely based on our theoretical models and ceased trying." The gap was not in scientific knowledge, but in the willingness to pursue development despite theoretical obstacles. The strategic implications were profound. Battle of the Atlantic. Centimetric ASV Mark III contributed decisively to the Allied victory in 1943. Strategic bombing, H2S, allowed accurate navigation and bombing through weather, improving night bombing accuracy from miles to hundreds of meters. Night air defense, centimetric AI decimated German bomber forces, effectively ending the German strategic bombing campaign against Britain by mid-1943. The cavity magnetron was a paradigmatic example of technological surprise. Theoretical miscalculation. German calculations predicted the magnetron would be unstable and low-powered at centimetric wavelengths. British experimentalists found practical solutions that German theoreticians declared unlikely to succeed. Industrial mobilization. The tens of thousands of magnetrons produced by Allied industry dwarfed German production of hundreds over the entire war period. Allied production systems transformed advanced technology into an abundant commodity. The small copper cylinder captured near Rotterdam in February 1943 represented 5 calendar years from the British breakthrough in 1940 to German limited production in 1945 of technological and industrial advantage that Germany could not overcome. It was evidence that warfare had entered a new technological domain where industrial capacity to manufacture advanced electronics at scale was as important as armies in the field. Today, descendants of the cavity magnetron generate microwaves in millions of kitchens worldwide, a testament to a technology that decided the electronic warfare battles of World War II.